All right, guys, welcome back to another edition of Math with Matisich. I got a little bit of stuff here to do today. What we're really going to focus on, hoping you can see this pretty well, we're looking at three different functions: linear, quadratic, and exponential. And the goal really of this video is to identify which one you're working with. And I underlined linear and exponential because we're actually going to come up with their expressions as well. So let's get into it. I've got a few different functions laid out already. If you want to, you probably pause the video and make these tables and graphs and kind of work through the rules as I do in some type of note-taking device. So anyhow, let's get started with the first one. So to identify, if something's giving you a picture, the first thing I would do anyways is organize that information into a table. I didn't provide any pictures or anything, but here's a table for some expression, and we're going to figure out which one it is. So I think a good starting point in any table is find the change that it takes to get you from one y value to the next. So we're really just looking at like the slope or the constant rate of change first to see if there is one. So this thing, we go from 3 to 6 to 9. So if you really just think in terms of addition, to get from 3 to 6, I'm only going over one here, so I'm only looking at this column. To get from 3 to 6, I have to add 3. All right, and then to get from 6 to 9, I would also have to add 3. So whenever that's constant, whenever this stuff is constant, whenever you have a constant rate of change, I'm gonna write it out real quick, a constant rate of change, anytime you see that, you know right off the bat that your function is linear. Now, another thing you could do to check for linearity is plot the points. So I've got a coordinate plane set up. I only have quadrant 1 because all my values were positive. So if I go about plotting these points, I go over 1, up 3. Okay, so I just plotted this point right here. Moving on to the next point, I've got 2, 6, over 2, up 6. And then I go to 3 and 9, over 3, up 9. So whenever you plot your points and you try to connect them, you should see certainly a pattern forming. It is forming a straight line. And that's another good indicator that the expression or function that you're working with is linear. So a couple different strategies to use there. Like I said at the beginning of the video, we are actually going to try to come up with the expression that gives you these values. So what's the rule that gives you these 3 points, or really anything on this line? So a couple things you can do is, maybe the easiest thing, and that's why I left this thing blank. So here's a slope-intercept form for a line, y equals mx plus b, where x and y are just points on the line. M is known as the slope, or like I wrote over here, the constant rate of change. And then b is the y-intercept. Okay, so if we try to come up with the rule, like I said, the easiest thing to do is, well, where does my line cross the y-axis? Where does it cross the y-axis? That is going to give you the y-intercept. So using the graph that I made, you could probably deduce what this is, but if I go back to my table, when x is 0, that is when I cross the y-axis. So what would the value be there? I definitely didn't draw this line very well at all, but that's okay. What would I have to add here to get to 3? I mean, this is constant, it's never going to change, so I'm definitely going to have another plus 3 right here. So you could think of it as, well, hey, what do I add to 3? Or if I add 3 to something, I get 3. So hey, that is going to be 0. So the y-intercept here, this b value, is just 0. So I know I'm adding 0 off to the end here. I should probably fix this a little bit. Like it never happened. Awesome. X and Y, as we said, they can change. They definitely change. You see that they're changing their variables. So those are still going to be there. And then the slope, we already figured out the slope. We are going up 3 over 1, which really just simplifies to 3. Of course, you don't really need the 0 there. And we're only working with expressions, so don't even need the equal sign. This would be your expression, 3x. That's what you would do like on your homework assignment. If there was a y-intercept, then certainly add plus or minus whatever that constant amount was. So that's it for linear. Make a table. I think those help. Look for a constant rate of change. And you get the y-intercept, either plug in 0 or graph it, see where you cross the y-axis, continue the pattern up to 0. There's a lot of different ways to get the y-intercept. I'm not going to focus too much on that. That's like Algebra 1 stuff, right? So hey, let's move on to the next type here. Like I said, whenever you have your table, try to look for a constant rate of change first. So let's do that. Hey, to get from 1 to 4, I would add 3. To get from 4 to 9, I would add 5. That gives you a clue on what this one is. It's not 3. So this expression, this function is not going to be linear. If I do the next one, I'm adding 7. So nothing constant in that first rate of change there. So what we're going to check now is the second rate of change. Second change. So to get from 3 to 5, I go up by 2. Add a 2 to get from 3 to 5. And then to get from 5 to 7, this second change was also 2. Okay? So when you see this, and this has a name, it's not a constant rate of change, this is a constant. When you see a constant second change, anytime you see a constant second change, your expression, your function is going to be quadratic. Just write that in here real quick. Constant second rate of change, you have a quadratic function. We can plot these points too, just so you know what this graph is going to look like. So I go over 1, up 1. Just be careful with the scale that I use. I went up by 3s this time instead of just going up by 2s. So anyhow, I went over 1, up 1, over 2, up 4, over 3, up 9, over 4, up 16. So it starts to increase pretty quickly. And then I'll just try to connect these dots. It's going to look like this. Try to make this one look a little nicer, more accurate. Okay, so there's 1/2 of this graph. Maybe you taught or learned about this in Algebra 2, but these things are actually reflective. So we're going to have another piece going this way at the same rate. Okay, and then that graph right there is called a parabola. Now the quadratic ones, we're not going to worry about too much right now. I'll teach you how to come up with their expressions later. For what it's worth, though, the general form would be y equals ax squared plus bx plus c. Not going to worry about coming up with these expressions right now, though. That'll be a couple weeks from now. So the quadratics, look at a table, try to find the second rate of change, or graph it. And if you create this thing, which is called a parabola, so if you graph your expression, your function, whatever, and you come with a parabola, that'll also tell you that you have a quadratic function. Okay, moving on then, this last one. So I know I said try to look at the first changes. So we go like from 2 to 6, we add 4. From 6 to 18, you're going to have to add 12. And then you can look at the second rate of change. If that's not equal either, then it's obviously not linear or quadratic. So another thing to look for in a table, and I think you can try, is to look for a constant multiplier. So to get from 2 to 6, you can multiply 2 by 3. And then to get from 6 to 18, if I took 6 multiplied by 3, you would get 18. 6 times 18 is, or 6 times 3 is 18. 18 times 3 is 54. And let's do this one too. 54 times 3 is 162. So it's not a constant rate of change this time. It's not a constant rate of change. This has a constant. It has a constant multiplier. Constant multiplier. So if you're multiplying by a constant amount instead of just adding or subtracting, multiplier, you have a constant multiplier, then your expression, your function is going to be exponential. Let's see if I can actually spell this right. E-X-P-O-N-E-N-T-I-L. Exponential. Constant multiplier means you have an exponential function. So let's graph this one too, so you can get a good idea of what this one looks like. I change the scale of counting by tens because it just increases exponentially. I go over 1 up to somewhere about like right here. And then I go from 2 to 6, maybe like halfway up. And then I've got 318. I'm starting to jump up pretty quickly now. 4 to 54. Somewhere about right here. And then for 5, I jump all the way up, somewhere way up here, up to 162. That's all we need though. So your exponential function, it starts incredibly slowly, kind of follows that axis for now because I don't have anything else. So exponential functions, they're graphs. You're going to have a nice smooth curve that increases very, very sharply. And it would just keep going up. This is what an exponential graph would look like, or the graph of an exponential function. Okay, so the last thing to do on this is come up with the expression. What gives you these values? What gives you this y column? What can I plug in to give me 2, 6, 18, 54, and then 162? So the form that we're going to use for now is y equals a times b to the power of x. So that gives you a hint right there, right? The exponent is our variable. It's an exponential function. So a is your initial value. And then b represents the growth rate. Then again, x and y are variables. Those things are going to change depending on where you're at. The growth rate. Okay, a initial value, b growth rate. So the initial value, that's going to be pretty easy to find. We started off here with a value of 2. That'll be our initial value. So y equals 2 times, now the growth rate is this constant multiplier. We were growing by a rate of 3, multiplying by 3 every single time. Okay, and then up here in the exponent, like we said, x is just going to be our variable. Now this is almost correct, but we got to think about what we're multiplying by 3. So like at 6, we multiplied the previous term by 3. We multiplied 2 by 3 to get to this value. To get 18, we multiplied the previous value, 6. 6 times 3 is 18. So how you'll write that out algebraically, we're multiplying by 3 times the previous term. So you are going to take the previous term by subtracting 1. 2 times 3 to the power of x minus 1. And we can verify that that works really easily. So y equals 2 times 3 to the power of x minus 1, right? That's our expression, our equation for now. So let's pick this point. Let's make sure this works. So we're going to plug in 3 for x and 18 for y, and make sure it actually equals out correctly. So y again was 18. 18 equals 2 times 3 to the power of 3. Right, that was our x value. That gets 18. X value here, if I plug in 3, I should be getting 18 out of it, minus 1. So we can go about simplifying this now. 18 equals 2 times 3 to the power of 2. So I just simplify my exponent. 3 minus 1 is 2. 18 equals 2 times 9, because that's what 3 squared is. 3 squared is 9. 2 times 9 then is 18. 18 certainly does equal 18, so our expression works out just fine. All right, so that's how you identify. Key points to remember: linear will have a constant rate of change, a constant first rate of change. Quadratics have a constant second rate of change. And then exponential expressions or functions have a constant multiplier. Those are the difference. And one more thing, of course, is we want to try to come up with these expressions for linears. We're going to skip expressions for quadratics, and then exponentials are right down here. Y equals a times b to the power of x. Shouldn't have too much troubles with this. Initial value, growth rate, and then make sure you're using the previous term, not the term that you're at. Okay, hey, let me show you your book real quick. I'm going to go there and show you kind of stuff that we need to be able to do. So here's the book. We are on page M1-24. So hey, the situation is 3 people know the winners of the homecoming election. And then each one of those people tell 2 other people, and then the pattern continues. So we started off with 3 people knowing the secret of who's going to be the winner. Each one of those people tells 2 people, and you can see that it's growing pretty quickly. So analyze the pattern, come up with things that you think are important. And like I said, man, tables will really help you out with these. So complete the table, summarize the number of seniors who learn about the election result each day, then write an expression to represent the number of seniors who learn about the election results on the nth day. So we're kind of coming up with an expression there. Okay, hey, so if we do the, let's do the table first. So we started off on day number 1. We've got 3 people that know about this secret. So right here, number of days that pass, 3 people knew about it. Okay. If we continue on day 2, it looks like there's 1, 2, 3, 4, 5, 6. So 6 people here. Day 3, we got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay. So for days 4, 5, and 6, we have a strategy we can use. We can keep this picture going. You know, like draw 2 more things here, a couple more stick figures. I do the same thing for this guy, and just do that until you get to the 6th day, but it seems like a lot of work. What would be a lot easier is probably just continue this pattern that we've got. So it definitely looks like we've got a growth rate, something we can do to 3 to get to 6, and then do to 6 to get to 12. Pause the video if you haven't figured it out yet, but what you can do is multiply by 2. 3 times 2. 3 times 2 is going to give you 6. 6 times 2 is going to give you 12. And you can keep that pattern going. 12 times 2 would give you 24. 24 times 2 would give you 48. 48 times 2 would give you 96. So you can see, hopefully, the importance of coming up with a pattern helped us out a lot there, not having to draw out that picture. So let's go on. Actually, let's go ahead and get the expression down. So since we have a constant multiplier, hopefully you know what type of expression it is. This would be exponential. Exponential. Again, why? It's because we have a constant multiplier. So here's our form that we're using. Y equals a times b to the power of x. So hey, what's the initial value here? We started off with 3 people knowing the results. Multiply that by our growth rate, which was what we're multiplying by, which is 2. Multiplied by 2 every time. We have our variable here. It actually wants us to use n, so I'm going to replace x with n. N represents the number of days that have gone by. So let's replace x with n. And again, we're having to multiply the previous term by 2. So to get there, you subtract 1 from n. We're multiplying the previous day's total. So that pretty well answers that question, I think. A couple more things on this. Yeah, we'll go down. So you're going to graph it. You should get a curve out of that, a good smooth curve. For does everything in that curve make sense? You would answer probably not, because I mean, after like 2.5 days, you're going to have like this decimal amount of people, which definitely doesn't make sense. So we're really restricted to whole numbers only. We already talked about number 3. It would be exponential. Key characteristics. What did we have again? We had a smooth curve that was increasing very, very sharply, which indicates that it is exponential. You should be able to answer this from your table or use the expression that we created. On the 12th day, you're going to get this extremely high number where it probably doesn't make sense either. There's not that many kids in the school, I would bet. And that's really going to do it for this video. So again, the most important things was how to identify each expression. and developing a rule for linear and exponential. Hey guys, thanks for watching, and I'll see you in class sometime. Bye-bye.